Okay, we can start. So, if there's anyone still willing to join, they can do so. Or we can start our session. It's already like 4. Yeah. So today, so we will be discussing on uh, yeah, this orbital and spin angular momentum in quantum mechanics. So so this is what this was your important topic in your past week, which was covered in week 3. There you must have seen various lectures that have been uploaded on your NPTEL portal, and so hope you will be going through them. And yeah, if you are finding any difficulty, please let us know that we can help you out in solving any issue in understanding things or any concepts. So so we'll basically again we'll look into some basic problems, particularly related with orbital and spinning momentum. And we'll see. This is very important because that is going to be useful in various other upcoming topics. And yeah, this is one of the central topics, particularly when you talk about spin and quantum mechanics. So yeah, okay. So uh, orbital angular momentum. I hope you know them at least in some way from your first quantum mechanics course, your basic quantum mechanics course. Uh, but just again, a short review of that we can have right here, and then solve some other important problems. Uh, so, so classically, angular momentum is something given as um, cross product of position vector and momentum vector. So this is what your, uh, generically the angular momentum that you are familiar with. Uh, but in quantum mechanics, again, as we know from the first principle that we always like keep on those things. So where we consider this any operators or any any physical observable from the first principle of quantum mechanics, we promote them to operators. So here again, classically or generically, how we define angular momentum is a cross product of position vector and momentum vector. So you make this position vector a position operator, and momentum vector is momentum operator, and then you have your angular momentum operator. So that's how it has been so far. I hope you've been seeing this kind of things from the beginning, and that is what we'll keep on doing this. From where we'll find out how observables work in quantum mechanics. So that is how this angular momentum can be defined for any given quantum mechanical system. So, and on top of it, there is one more angular momentum that we will define, that is spin. So, we'll be coming to it very shortly, and this in Cartesian form, like this is how you can write. Uh, this is your um, yeah, this is your angular momentum for your x component, your y component, and your z component. So you write this again. These are all your operators. So in spherical components or in spherical coordinates, this can be like your spherical coordinates basically. I mean, uh, in spherical polar coordinates, these are basically x you can basically x you transform to something r cos theta, not cos theta. It is sin theta, cos phi, y r sin theta, sin phi, z you transform to r cos theta. Yeah. So when you go from this x y z to r theta phi in uh, polar coordinates and spherical polar coordinates, you can transform each of this component y, pz, and z, py, something into this. So basically, you first do L equals to r cross p in uh, r theta phi coordinates, and then you separate out the ij components out of it, and that will be your xyz components in for your angular momentum in spherical coordinate, spherical polar coordinates. So yeah, and your total angular momentum will be this. So yeah, so this is again, I think this has been uh, given to you, or has been taught by you by the instructor, like in your lecture videos that has been uploaded. So so you can go and check them out, and also yeah, this is something in your quantum mechanics level 1 course also you come across very often. So so just a preview of that, and again some more features of these operators. um, so if you are having any doubts or questions on these forms, you can ask, like uh, anything that that is not clear. Uh, Feel free. So, so I was telling, with these operators, you have some properties of quantum. Of this angular momentum. So, so suppose you see, this angular momentum Lx Ly, they do not commute. So, if you take commutator of Lx Ly, you get something Lz. So like we will try to show how this is happening, and when L by Lz commutes, you get Lx operator. So that means, like physically, what you can say that the whenever Lx Ly, you are doing any measurement of Lx and Ly. So you are doing some angular momentum measurement on a quantum mechanical system. So first you are trying to measure Lx, and then you are trying to measure Ly. So so they then that means that system that you are measuring, that is not in a given particular eigenstate. I mean, Lx Ly do not share common eigenstate. If they are zero, if the commutator gives out to be zero, then you get Lx Ly commutator to be zero. Then that means Lx Ly operator share common eigenstate. But in this case, they do not. Uh, so same you will find when if you take the commutation of Lz and Lx, you don't have zero, but rather you have is bar Ly. And but if you take commutator of L square with Lx, L square Ly, and L square Lz, you get zero. That means when you measure L square and Lx, like there I mean you there are no with certainty, you can say that they both share the common eigenstate, and and there will and the uncertainty associated with those measurement would be zero. So it means that you can simultaneously measure those things, like Lx Ly. They, since they do not commute, you cannot simultaneously measure them. Like there will be always some great uncertainty. But if you are doing L square Ly, or L square Lx, or L square Lz, you see from here the commutation is zero. So physically that means that you can simultaneously measure both L square and Lz of the given system, of the given quantum mechanical system, without any uncertainty. So you can certainly measure, because this commutation, if it goes to zero, it means that both eigenstate of L square and Lz, both are same. Basically they share common eigenstate, because of which because of you can calculate the I mean you can measure both observables at the same time simultaneously. But it is not so when you try to measure simultaneously Lx Ly or Lz Lx or Ly Lz. So right. So the eigenstates, how it is denoted. These eigenstates, the eigenstates of uh, L square or Lz, as you can see here, L square and Lz, they the commutation gives zero, and they share common eigenstate. So that means the eigenstate corresponding to L square or Lz, it is denoted as Lm. So this Lm are basically I can uh, so this is a notation that is defined for the eigenstate ylm. So this is your wave function, or this is your eigenwave function, and it is in vector notation. It is denoted as get of lm. Why? Because if you write down this, suppose if I uh, okay, suppose if I write down this ylm, it would be something. Uh, so these things would have also derived in your lectures, so you can check them. So if any problem, you can always ask. So these are very lengthy calculations to show to prove how this wave functions uh, after all comes from the Schrodinger equation. So when you solve a spherically symmetric potential, you get this wave function. Uh, so yeah, this is your complicated looking, but this is only for m greater than equals to 0. So if I write for ylm theta phi for m less than 0, it would be something this 2l1 2l plus 1 over 2 l minus 1 l minus mod of m l plus mod of m factorial then pl mod of m cos theta ein phi m less than 0. So yeah, these are your these are your wave function for the eigenwave function. Uh, Eigenwave function for L square and Lz operator. So where this uh, these are your like associated Legendre polynomials. So these are your special type of polynomial function which appears in these wave functions. Legendre polynomial. Okay, and yeah, so this basically appears. I mean, this kind of a wave function you get. Suppose if you solve a system of spherically symmetric potential, like I mean, how you solve like suppose your quantum system is a harmonic oscillator system. So you know some potential is v of half k x squared, where k can is your m omega squared. That is your uh, parameters of your intrinsic parameters of your given harmonic oscillator system, and you have also solved some systems like where V is zero, like for free particle, or a infinite well potential where you have potential is infinite all throughout the space other than a small region where it is zero, from zero to L. Otherwise, it is infinite for uh, all other values of x. So, and somehow like you also have some other potentials. Suppose like you have a system like hydrogen atom system. So where you have potential like k minus k over r. So so in this case you can see that your r, if you write this in spherical polar coordinate, v of r theta phi is just minus k over r. That means your potential is independent of theta and phi. They are that means they are uh, like spherically symmetric. So in that case, if you solve Schrodinger equation taking this potential, then you can derive this. You can get this wave functions. Those are your wave function corresponding to L square and Lz. So yeah, so whenever you have this kind of these are also otherwise known as spherical harmonics. I can write this spherical harmonics. Okay, any questions you can ask? Uh, like, did you all got or any problem or anything? So this is just a brief idea. So then, yeah, I was telling these are your spherical harmonics. These are your eigenstate, angular momentum eigenstate. So, so then what happens if you operate L square? You get this eigenvalue, and yeah, and since they are eigenstate, you will get the state back again. And if you operate Lz, and since these eigenfunctions are also I mean, these are also eigenfunctions of Lz operator. So if you operate Lz, you get M H bar. So uh, yeah, so and you can see maybe is there something. Okay, just wait a second. Okay, so right, then what we have this eigenwave functions. Right. So yeah, this wave functions like this YLM. If we're talking about this wave functions YLM theta phi, they are normalized. So basically, you see this overall factor right here. Uh, these factors are basically your normalization constant. So So if you basically take this integral, or basically if you want to check the normalization condition, so the normalization condition for these wave functions are usually this. So you have y ln uh, theta phi and y l bar m bar theta phi. So you take the complex conjugate basically on one, and you integrate them. So yeah, you will get something delta LL prime and delta MM prime. So you note one thing, in all these wave functions that which I'm writing down here, they are depending on two things. So depending on two integers, two quantum numbers. So one is your L and other is your M. So this is different than the wave functions that you have come across, like for infinite well, or for or what, like the harmonic oscillator, where you generally only had one quantum number n. But otherwise here in this cases right discussed here, so you have for example the eigenstate of angular momentum, you have two quantum numbers. They depend on two things. uh, were there any question? Hello, is there any question? You can speak. Okay, so yeah, these are normalized, and the normalization conditions are given by this. So yeah, so remember, like as I said, you note like they depend on two quantum numbers, L and M, unlike harmonic oscillator wave functions, or the wave function, the eigenwave function that you know about, the eigenwave function of Hamiltonian for harmonic oscillator system, like they depend on only quantum number n. So, but here you see the quantum number depends on two quantum numbers. Those are L and M. So, so similarly, so in quantum mechanics, what you have more is spin angular momentum. So this spin angular momentum, like it is like for a quantum particle, it is very, I mean, like difficult to imagine like how the spin quantum number would be there for a quantum particle. Like for example, we know for a point particle, we don't have any spin for that, in the sense that a like a point particle, like how we define spin or something, like for example, if it's a solid object, if it is rotating about its own axis, that means it is spinning, or it has some rotation. But for a point particle, rotation about its own axis, it is something not very meaningful, because it is a point particle. So so it's like, if you try to calculate, like if any rotating or a spinning object you take, like a spinning top, if you calculate the moment of inertia, you get some non-zero moment of inertia. So that gives you the the some intrinsic measure of the rotation or the spinning of that object. But if in case of a quantum particle itself is a very point particle, or it's very vague, that if you consider something, it is spin, because it is itself a point particle, and what is the moment of inertia for that. So it's something not well defined, but still there is something intrinsic associated with all quantum particles. And you have seen that, like also there were some lectures in your classes that you have gone through, where particularly the start of the your week 1 somewhere, you have seen this Stern-Gerlach experiment, like where you found exactly what is the other inherent feature of quantum particles, and that is they possess a spin, which is uh, one of the important important property of every quantum particle. So every quantum particle is associated with a spin. Like for example, when we define classically any particle, there are some we assign some particular what this I mean we assign some particular properties to that point particle or whatever the so those are like what are its mass and uh, like how yeah, like what energy it has or all those things. But in quantum mechanics, like on top of it, even if it is a point particle, a quantum particle, you still define something mass, but also on top of it, there also they possess also something called spin. So yeah, so the spin angular momentum. So if you look into its mathematics, that how we have seen for orbital angular momentum, the same thing that can be said for spin angular momentum. So here the spin eigenstates can be written as SMS. Similarly, how the uh, this orbital eigenstates are written here. The same way we can write S and MS, where S is your one of your quantum number and MS is the other. Just like how you have for orbital angular momentum, those are Ln. So you now you denote with S and MS to distinctly identify them as that they are related with spin angular momentum, not with orbital angular momentum of the quantum particle. So and similarly, the you can define the eigenstates in this way. If this, yeah, these are your eigenstates. So if you operate your operator on these eigenstates, so S square eigenstates are SMS. So that means they will similarly give you MS plus one S bar SMS. So something similarly what you found here. So they give uh, L times of L plus 1 S bar square Ln. So here also Ms of Ms plus 1. Uh, oh no, this won't be Ms, rather it would be S. Yeah, so you can see here. So since they follow same algebra, just like how orbital angular momentum, because like uh, if you see, I mean, dimensionally they are the same things. So uh, that means here you see that here when L square operates, you get L times of L plus one. L is known as principal quantum number, or not principal, or yeah, but these are I hope you know for each L your ML for for each given L, your ML values goes from minus L to L. So minus L, like if your L is two, then ML would be minus two, minus one, zero, one, and two. So just like that, here also the same thing. For every S, your MS value will go from minus S to S, and there is also a SZ operator uh, whose eigenstates are also SMS. So if you get operate this one, you will get MS H bar SMS. Right. So now these are some some few things. If you remember or you keep this in your mind, then we can try to solve some questions right here. So before that, if any doubt or anything that was not clear, or any kind of issue, uh, any problem, or You people can able to hear me, right? My voice is clear, right? Uh, Hello, Hanuman. Uh, Hello. Oh, okay. Thanks, Nitin. So yeah, mm, so right, we can see some uh, questions right here. So first, let's say uh, prove the competition relations. So one. So this is the one which I initially was telling. So they LX operator and LY operator, they do not commute. That means they do not share a common eigenset, and you cannot measure them simultaneously for a given quantum system. Like if you measure them, like you will get something. I mean, there will be uncertainty. So with I mean, you cannot measure them simultaneously with certainty. So that is why you get non-zero commutator. This is not zero. So to prove this, like this is something not non-zero, and this is basically LZ operator. So let's start with how we define LX operator. Basically, how generically how define LX and LY LZ for classically how we define. That is how we can start here, and we treat them as treat those position variables or momentum variables and operators, and then we proceed. Yeah, so LX, LY, LX is we defined at the beginning. That is y times px is an operator x py. Then uh, z px and x pz. Yeah. So yeah, something what at the beginning what we wrote down. These are your LX, LY, and LZ. Yeah. So if you uh, yeah open this commutator, and then if you keep on, so if you uh, solve it term by term, like by let's first take YPX, then ZPX. So first, to evaluate this commutator, you first take this and this, then uh, this and this, to take minus of uh, YPX, then XEZ, then yeah, then you take this and this, that will give you minus XPY ZPX, then yeah, then the last ones, which will give you plus of XPY and XPZ, right? Then you can see here, if I uh, there is like from another fundamental relation that you know, which is if you are familiar, I mean this, you should know this, like this is your very fundamental law from where Heisenberg uncertainty is proved, that commutator of position and I mean position and momentum operator is always something will give you IH bar. So this, or same as YPY. So this is basically your Heisenberg uncertainty relation. So that means you cannot measure position and momentum simultaneously. So y, but otherwise, if you measure y uh, component of the position and x component of the momentum, this will give you zero, which means you can simultaneously measure y component of the position and the x component of the momentum simultaneously. They share common eigenstrength. So using this right here, what we can do, um, uh, suppose if you pz, this is actually I've done a small mistake here. So this is not x, this is basically z. Uh, this is y pz and z dy. So I think I have to change here also. This is z, and right, and then you have y pz again here, right? Then z to y. This will be your z. No, this. Yeah, I think now this is fine. Yeah. So if you see the in first, yeah, if you see this in the first case, you have in the first term you have something pz and z, and then similarly you will get uh, uh, there is y ypx. Yeah. Also in this case, you see you have x and px. So now, using this properties that which is here, you can show uh, that I can write this. You can check this out. I can write this compared to the first term. This will be something y uh, p z z p x, and yeah, and you can check this out. Even this thing which is right here, I can write it as something y p z x p z, where this is basically your zero, and this is basically your uh, pz and z will give you minus ih bar. And yeah, same way you have minus the third term. From third term you will get uh, probably again x, and you have x and dx. Uh, uh, yeah, from y piece, from this second term you got zero. Then from the other term you again have ex py, but it's px py, xpz. ZP. Uh, is there some mistake I done? Yeah, again, this should be Z. I missed out again. Yeah, initially that mistake which I did. So because of so right, this is Z. So yeah, so initially as I wrote this as EX and X, but it should be PZ and Z because that is how LX is defined. So yeah, so because of that there were some confusion. Now I hope this is gone. Yeah, now yeah, from here again I think you will get uh, yeah, you will get zero again from here because I can write this as uh, Z Py and Z Px, which is again 0. You can see the commutation properties that is on here. But then you have the last term. From last term, you will get again minus of I h bar, uh, minus of I h bar, uh, uh, Py and x. So this you can write down finally I h bar x Py uh, minus ypx equals to I h bar lz. So that is how you show. So is this clear? Any problem here? Understand? Is it clear or any doubt or any issue with it? You can tell. Yeah. Any problem? Okay. Fine. So then next again you can show one more thing, one more computation where second you can take uh, LZ commutator with L plus. This should give you H bar L plus. Now, what are L plus? Like you have L plus and L minus here in Anglo modem, just like how you had A dagger and A in harmonic oscillator. So they are raising operators, raising and lowering operators, or rather, they are called ladder operators. So ladder operators in quantum mechanics, I mean ladder operators in Anglo modem, or something has same purpose, just like how you show them in harmonic oscillator. So ladder operators are L plus and L minus. So now how they are defined? L plus is defined as Lx plus ILy, and L minus operator is defined as Lx minus ILy. Then right, yeah. Then so as the name says, raising operator. This L plus is your raising operator. So when this operates on Lm, they give you something L m plus 1, just like how it works for harmonic oscillator. It's the same way when L minus operates on Lm, you get uh, L m minus 1. So yeah, and there are other things when L plus x on Lm, uh, where Yeah, or yeah, that's it. What uh, you have to show you else when what happens when LZ and N plus commutes. Yeah, they do not commute, rather they they give some non-zero commutation. So that is what you have to prove. So so let's start with LZ and L plus is, as I said, they are defined as LX plus ILY. If you take this computation, then you have LZ and LX plus I LZ and LY, right? Then uh, LZ and uh, yeah. So LZ and LX, as I told you before, this will be IH bar LY. So I mean from here. Sorry, not from here. So LZ and LX, like from the beginning, as I told you. So LZ and LX commutator, it gives you IH per LY. So taking that, you have IH per LY plus I LZ LY similarly will give you minus IH bar LX. So from there you get IH bar Ly minus or this minus I are will give you minus 1, and yeah, I square basically gives you minus 1 and minus 1, and then you already have another minus, so that is plus. So from here you get h bar lx, and this you can write it as h bar lx plus I ly, and this is again nothing but your h bar l plus. So yeah, so then you finally have lz l plus is h bar l plus. Okay, then uh, same way you can also show there is one more relation where uh, if you follow the same process, you can also prove LZ L minus will give you minus H bar L minus. You can check this one. And there is one more which we can check right here. When L square acts on L plus, it will give you 0. That means if they commute, you can simultaneously measure uh, taking these two operators. So, and if you see how you can quickly prove this, so this is easy to show. So this is Lx plus ILy. So L square Lx operator plus I L square Ly operator. So yeah, and L square when operates on Lx, that is 0, and I times 0, that is 0. So yeah, L square and Lx, as I showed you at the beginning, that they commute L square Lx. Their commutation is 0. So again, to prove this, how L square Lx is 0, you can start like take this Cartesian form of these operators and prove them. And for that, you have to you need this Heisenberg computation relation, this uncertainty xp xi h bar, just like how we proved this IH value LZ for the computation of LX and LY. So yeah, those were some computation properties to prove. But yeah, then we can look for some other questions. For example, uh, maybe uh, related with some spin, or maybe yeah, or let's say something. Take this on the ladder operators for angular momentum is given as L plus or minus. So if there's any problem or anything, please ask. Uh, so yeah, so this angular momentum, this ladder operators is defined this way, as we also, saw in the previous part. But in Cartesian, this is how they are defined. So I mean, in spherical polar, this is how they are defined. So now the action of LZ operator on spherical harmonics. Uh, so spherical harmonics means basically YLL, your YLM, which is function of theta phi basis, uh, given by LZ YLL, H bar L Y L L, and L plus Y L L equals to 0. Then determine YLL theta phi up to a normalization. So, uh, yeah, so you you can see. The question is basically, your L plus L minus ladder operators are given for you, and then your LZ operator. But when it acts on YLM, that is YLM theta phi, and it acts on this, when LZ and L plus acts on YLM theta phi, right here, they give this uh, result, which means, where you can see this, when LZ is operating on YLM, so where it is particularly acting on one specific YLM state, where M is basically equals to L. So you see on top of it you have M, on top of it you have L. So when this LZ acts on that particular YLM, where M is equals to N, M is equals to N, then you get this H bar N, YLN, and when L plus X on it, you get this 0. So then you have to compute. Uh, so one idea you can get from here, that it is obvious that when L plus will X on Y LL, it has to be 0, because uh, I mean as I said, m can go from minus L to L. So the maximum state for uh, the, I mean, we write Lm as for YLM. So the maximum LM state, it can be LL. So if L plus will act on this thing, it has to go to zero because there is no other state above it. So beyond LL there is no other state. So that is why when L plus X on YL, it gives you zero. Yeah, and also this thing, this factor which is right here, that you got when LZ acted on YLL, you got H bar L and YLL. So H bar L, you can again, why it is so, you are getting again, you can know from the definition that we started with. So right here, this one right here. So when L square acts on LM, you get this thing. So L times of L plus 1 H bar square. uh, uh, Sorry, that was L square, LZ. So in question it is given for LZ. So this is when LZ acts on LM, so you get M times H bar. So your, since M is equals to L for the case which is given in the question, so it has to be LH bar. So this is LH bar, and this YLN are basically your LN. So right. So then you have to calculate what is your YLL. You have to evaluate this. You have to determine what is YLL, the wave function. So to have to know that, what we can do, we can start with. So yeah. So the action of LZ on YLN gives you H bar L YLL. Then that means if minus I H bar del by del phi YLL. So this LZ operator is basically equal to, I mean, yeah, it's basically equal to this. So, and yeah, this is something again at the beginning I showed you that in Cartesian, or in spherical model, this is how it is defined. So yeah, so if you in Cartesian, you write this Lx, Ly, Lz, the operator forms. I mean, you simply have the generic relation of components of angular momentum in Cartesian form, and then you transform it. You basically have to transform r cross p into, in terms of r theta phi, with this transformation rule that you know. So yeah, you can check this how relation comes, like they will be surely given in your lectures, or maybe in your uh, like books like Griffith. So yeah, so from there you find that your LZ is, you, in terms of spherical polar, you can define your LZ operator as minus I h bar del by del phi. So using that, you write your wave function. You that is your LZ operator. You write your LZ operator, and that acts on your the wave function YLM, or the eigenwave function, and that gives you H bar L YLL. So YLL is some unknown. It is some variable that you have to compute. It's some unknown function. So that means you have del 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 YLL of del phi with respect to del phi. You have I times YLL. So now you can. say your YLL is basically some uh, yeah. So if you solve this, you find f of theta e to the power IL phi. So you solve this simple differential equation. Uh, Solve the ODE, means the ordinary differential equation. You get, I mean, you will surely get this thing, and then there will be some constant, and you call that constant as f of theta. So this is your constant of the I mean the differential equation that you solve. So basically, to solve this, you, you can do, I mean, you variable separation, or whatever you call, I mean, like for example, del by ln. I mean, this is similar to the integral that you often come across, d by ln integrated d5, and then there will be some constant c, and that constant c is basically you write it as, you write that constant c as f of theta, because you're doing this uh, I mean, these are your partial differential equations, so they are not I mean the uh, absolute differential, that the total differential that we know, they are not total differential. uh, so they are not total differential, they are partial differential. So when you I hope you have come across this in your uh, math class or in mathematical methods, where you solve this kind of exact differential equation or inexact differential equation. From there you find that the constant is usually equal to the other variable that the function is dependent. So in this case, the function is dependent on two variables, theta and phi. So if you are solving with respect to phi, then the constant that you get in your, I mean, after solving the differential equation, the constant that you get, that has to be equal to something f of theta. So yeah, so call that constant as f of theta, then that will be yeah. So yeah, okay. Then the other, you use the other condition which is given, that is L plus acting on YLL is 0. So that means again you take the operator form. So use the Lx and Ly operator form. So again, use this Lx and Ly operator form to write L plus. So this L plus, or write it as Lx plus ILy acting on YLL equals to 0. So that means h bar ei phi del theta is I cot theta del phi f of theta. So YLL, you take this YLL, f of theta exponential IL phi equals to 0. So yeah, so you are taking this as your YLL, and yeah, from here you again you have another differential equation where yeah, where you can show the following. So e to the power IL phi del f by del theta. So just operate this on this thing. you get it, uh, plus if cot theta. Then you have to take with this derivative with respect to phi, so that will give you il exponential il phi, right? So that is equals to 0. Then again, yeah, you solve the differential equation. So you have uh, so yeah, this should be again something similar to this df by f over l cot theta d theta, and that will give you ln f l ln this cot theta integral, that is ln sine theta, and then we will have some constant. So yeah, then ln f equals to ln sine l theta. I can write this as, I can take this l as the power of sine because I have log, and then plus constant. And yeah, and this constant will not be any other function of theta anymore. Like as we said in previously when we were solving the previous differential equation, we said that this is f of theta. But this f of theta is used again to solve, used again in this condition to determine what is f of theta. So and in this point, at this point, you no need to use that. I mean, that constant is again something f of phi or anything else, because f of phi you already found what is, that is e to the power I alpha. But now you are solving with respect to theta, so you don't have any other unknown or unknown constant. So now it has to be some constant. It should be independent of theta and phi. So yeah, so from here you get what is f. You write that constant as something. Let's say something as k. Then you have ln f sine l theta, sine theta to the power l, that is sine l theta, that is how you write k. And yeah, then this f is basically, this f of theta is basically some constant. Let's say that constant is a naught, or something, yeah, a naught uh, sine theta to the power n, that is sine l theta. So now we finally have y ln theta phi as k tilde e to the power I l phi sine l theta, or basically this is I'm writing as n. Okay, so any a question or anything, any problem you can tell, anywhere you could not found anything, you missed out. Is there any problem or, okay, if there's no other questions, we can move further. uh, Okay, so then so next we can try to discuss. So you people are like taking the, I mean, you are registered for this course, right? Uh,
Yes, sir, we are registered.
okay, registered. So so you are going through the lectures, right? Like,
Sir, we have not enrolled. I have not enrolled in the exam, but I will be enrolling it in a day or two till before the last date. I have gone through some of the YouTube videos. This
okay,
is my first lecture. I could understand some of it. I will go back to the PPT slides and will cover it up.
okay, okay, okay. So, yeah. So if any problem you are facing, like, let us know that if you are unable to
Sir,
understand.
sir, I have some issues. As you mentioned in the lecture, spin angular momentum.
Yeah, yeah.
So, if spin angular momentum, let us take there is a ball, and a
Ah,
cricket ball or any ball or football. When it rotates, we can understand in a classical sense that it will be rotating, it will be having some inertia, and that we can calculate through Newtonian mechanics.
yeah,
But
yeah.
how in quantum mechanics spin angular momentum makes sense, because we cannot tell that when the body is moving at what speed and at what place. So is it just a probability estimation, or what does it imply? It's very difficult to comprehend the spin angular momentum.
So so it is like what happens. Uh, Let me. Yeah, I'm saying that the spin angular momentum, that how you are trying to visualize, how you are imagining. So you are imagining, like, for example, an object is there and it is trying to rotate, or it is trying to spin around its axis. So that is what we normally know when we call spin, or something is spinning or something is rotating about a axis. So that is in a classical sense that
Hmm.
we know. But what happens if something, let's say, in quantum mechanics, that is not true. We are not calling something, let's say, electron. We are not calling electron is spinning around some axis. Electron itself is a very point like particle, I mean, very microscopic quantum particle. You know where you can, I mean, define, I mean, accurately its position. I mean, due to various reasons, could be uncertainty principle comes into, and other things. So you, first of all, you cannot exactly track the position, and then further, even if you have no if you track down electron at a certain point of the space, then you say that, like, if it is spinning, it has no meaning on that, because it cannot be, a point particle cannot make any sense if it is spinning. So this spin angular momentum is just some intrinsic, I mean, feature associated with it. So it's very and it is proven that it is not that we have been we have been I mean, getting delusion with something else, that it is some other quantity, or something else, but it is it is like, just like, for example, you have any like, classically, if you have any object, you define mass for it, you define some energy, you define also
Hmm.
momentum for it. Just like that, I mean, like, for example, electron, you define mass, you define charge, but there is something more intrinsic, more fundamental, and that is spin. So and that spin, if you mathematically see how the spin appears, from the if you do these calculations on the uh, on the foundation of quantum mechanics, you will find that this very mysterious quantity that we are calling spin, it actually takes the dimensions of angular momentum, just like how if you define an orbital angular momentum for the same thing. So, like, how we define fundamental property like mass and charge, just like that, you also assign one more fundamental property for a particle, that is spin, and it has dimensions of angular momentum. So if you're trying to imagine how, I mean, the spin is something associated with with its own rotation, it is not like that. And it is also proven from experiments like Stanza-like experiment. If you have not seen, I think
I've gone through it.
you have gone through, right? Yeah, so you have gone through a Stanza-like experiment, right? Hello.
Yes, sir. Yes, sir.
Oh yeah, okay, okay. So yeah, I'm trying that. Don't try to associate with that visualization. It is not exactly that. The spin is not the we are calling it a spin because we are calling it a spin angular momentum because its properties, its mathematical properties or mathematical dimension. I mean, dimensionally, if you lay down its mathematical framework, it goes exactly same as how orbital angular momentum, how you define orbital angular momentum. So mathematically, it takes the form or structure of some angular momentum observable. So that is why we are calling it as some angular momentum. Let's say call it spin angular momentum. But that spin has nothing to do with the understanding that we do know that it is spinning about some axis or something. It is not that.
Okay.
It's always going to be vague and counterintuitive when it comes to quantum mechanics. So there is no surprise about that. So yeah, it's like that. So
Okay.
so did you get my point? Like you can,
Then I got it.
yeah, yeah, you cannot associate that. It's like a notion or a idea of spinning top or a spinning object with a spinning point like particle for a quantum particle for a quantum like particle. So so that is what
Sure.
uh, yeah, some, if you got something else you can say.
Sir, we have to submit the assignments as well for the course.
Yeah, yeah, you have to. I think there are some deadlines or due dates, so try to
Mhm.
submit within those dates. So those I mean, assignment submissions are also key for your, I mean, course. I mean, because that will be a part of your certification. So so don't try to miss out. So I think you have an
So,
overall criteria that if you maintain those criteria, then you will be getting a certified course on this advanced quantum mechanics.
sure, sir.
Yeah, yeah. So you are yet to enroll, right?
Enrolled for the course, I have to enroll for the exam, and I think 11th or 12th is the last date. So tomorrow or day after tomorrow, maybe the last day. I will enroll it by the end of the day today.
Oh, okay, okay. So yeah, yeah. Try to enroll as soon as possible
Sure.
because I think week 4 contents are also already out, so it would be difficult to catch them all if you delay it furthermore.
No, no, sure. So exam will be on September, 20 September,
Yeah, yeah, yeah. That like I forgot the date, but the date would be around September, right?
after 1 month nearly.
Yeah, yeah. So follow the materials and contents. You will find it. You will get it.
Sure.
So you've also done some quantum mechanics course before, right? Or this is your first quantum mechanics?
I have done my BSc Physics honors 15 years ago,
Okay,
and then I'm self-employed. I was actually going somewhere. I just noticed a IGNOU notification that they have started MSc Physics. So at that
okay,
time, I wanted to join the MSc. I also got admission in MSc in waiting at IIT, but due to some financial reason or work
okay,
reason, I have to come to Delhi.
okay, okay,
So I have enrolled in MSc Physics in IGNOU. I'm self-employed. I'm not looking for
okay,
any job purpose, but that time I wanted to do, I could not do it.
okay,
So
okay.
there I got to know this NTPL and this, so I enrolled into it.
I see.
I enrolled it just a few days back. So I have the basic idea. I have to go back to the BSc Quantum Mechanics
Uh,
and then have to move on. So it's a long time back. I have almost forgotten everything, but still, since you told these operators, I still remember operators are some sort of exercises that is being done, and it changes the shape of the function. So
Uh,
all this I recollected. I have
uh,
studied them almost 15 years ago.
okay, okay. So yeah, the operators are basically like when you have like classically, you know, uh,
Hmm.
so classically you have physical observables like physical quantities like you have like momentum, you have positions. So you like for example, if you are given a classical system and you want to study the classical system, you will use some physical observable to measure
Hmm.
some of the quantities like momentum and position and velocities and all that. So but in quantum mechanics, you will not have if you want to calculate momentum, you cannot just calculate from position and velocity and all that. You have some state wave function which is that
Schrodinger wave equation.
yeah, Schrodinger wave equation. If any given system, if any quantum system that you are looking into, you have some wave function associated with that system that will describe the state of the system at every point of time, and its evolution is governed through Schrodinger equation. So given that the particular given potential and the total Hamiltonian, so the operators are basically if you for the given quantum system, if you want to measure some momentum, let's say, then you take the momentum operator and you operate that on the given state of your quantum system. So suppose your system is some electron trapped in a box, and you want to measure that momentum of that electron. Then first you deduce the wave function. First you calculate the state of that wave function of that electron which is trapped in a box, and then take that wave function, and that wave function describes the state of electron, and for that electron you want to measure some quantity called momentum. Then you take a momentum operator,
Hmm.
which is given as some derivative operator, del by del x, or minus I h bar grad operator. So you
Hmm.
operate that on the wave function psi of x, and then the whatever the result that you get, that will give you the momentum. So if that
But we have to learn back the matrices etc for it, or it can be done without that.
yeah, I mean, you need a little bit of idea about it because somewhere that will be useful. The thing is, like, you cannot always do with, I mean, using wave function way. I mean, there is this like uh, uh, Dirac way of doing quantum mechanics, like using Dirac notations where you use vectors and matrices, and yeah, using these tools, it is quite easy to track down the nature of quantum mechanics very easily. But if you want to always deal with wave functions and the Schrodinger way, like how using wave functions and operators as some differentials or something, you will find that at some point it would get very difficult. There would be very complicated wave functions, like one which we were discussing right now, just today in today's session, where we come across this wave function called spherical harmonics, YLA. So when you try to derive it from the uh, first principles from Schrodinger equation, take the potential and do it, you get this very complicated special type of polynomials like Legendre polynomials, then logger polynomials, and yeah, and very other complicated things that you will face. So it becomes very difficult to deal with this thing in this kind of functional. The notation that we use, the functional notations, that becomes difficult. I mean, it is easier to work with Dirac mathematics, which are using the principles or the basics of abstract vector spaces. So where you define the wave function as some state vector in a abstract mathematical space.
Got it. Got it. Got it.
Yeah.
Sir, can you recommend some good book on quantum mechanics
Uh,
right now?
which quantum mechanics?
This quantum mechanics that what we are studying right now.
Uh, yeah. Sorry, I couldn't. get your question well.
So, can you recommend a good book of quantum mechanics?
Oh, a book. Okay, so book. There are a lot of them. So if you want to start from basics,
Because earlier when I did my BSc from IGNOU, I have to rely on IGNOU books, and that time that they were very obsolete. They were not revised. Currently, it has been revised, but I haven't got my old IGNOU book. That time
okay,
I relied on Arthur Beezer Modern Physics
okay,
15
okay.
years ago.
Arthur
But now
Arthur Weiser is good. I mean, it is. I mean, easy to start. Like it is something you will get some foundational intuition, very nice. But that is not quite. I mean, sufficient
very
enough.
introductory level.
Yeah, yeah, yeah. But to start more freshly and with proper basics, I would recommend David Griffith. So
David Griffith Quantum
yeah,
Mechanics.
yeah. So that would be very, I mean, good to start if you are a starter, uh,
Hmm.
and you can follow Zetli. I mean, there would be some things would be a bit more detailed. So
Can you spell it Zetli?
yeah, Zetli. Uh,
Zetli. So it is for advanced quantum mechanics.
not that advanced, like I mean you will also get advanced content in that, but also
Mhm.
you'll get some basics, like I'm saying some few things, if you find it exactly it would be more in a detailed way, so that would help you to understand. So in Griffiths, like that is also fine, like I mean you will get most of the basics in a proper way. So and yeah, and there are more books like this Sakurai and Kointon, which is like they are bit advanced. So
Sakurai and
Sakurai, and then there is Kohen Tanorji. So like, and also there is book called by R Shankar. So R Shankar will
Arsenal.
be also nice, but then at some point you will find like things would be getting a bit complicated, but that is also a very nice book to follow. But I would suggest let's start with Griffith and Jet Li.
Sure.
Yeah, yeah. If you, and you have also done somewhat of uh, Arthur Weiser.
Well,
So
it was 15 years ago. I even do not
yeah,
remember the
I see.
integral of what will be the integral of sin x. It's, I think, minus cos x. So even I have to remember
Right,
that. I have
right,
forgotten
right.
differential, but I will cover it up.
Yeah, yeah, I see. I see. Yeah, I mean it will take some time, but yeah, gradually we'll find it. Uh,
So we will meet on next Saturday as well at the
yeah,
same time,
yeah. Every Saturday we'll be meeting. So
4 to 6 p.m.
yeah, 4 to 6 days.
So if I study and I have any doubts, I can come back to you with the same doubts.
Yeah, yeah, sure, sure, no problem. So,
Sure, sure.
so
Thanks.
anything like related to quantum mechanics or anything you are finding difficult with the course, like it's your just come in and discuss, like particularly if you are facing any difficulty, like just let us know right here. We can try to solve things.
Sure, 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 sure. Okay, sir. I shall get it myself enrolled in the exam, and I shall go through the course and shall come back with the conceptual requirement that I would be facing.
Yeah, yeah, sure, sure, no problem.
Sure, sir.
Uh, uh, okay, so if there's any other particular doubt, like I can also say right now. Uh, I mean, or if you want to ask it next week, then that's also fine. Okay, then probably we can do one or two more questions as we have some time right here. So let me see. Uh, Okay. So suppose for a spin half particle placed in a magnetic field, B, the Hamiltonian is given as H minus gamma, B Sy operator, or otherwise this is minus omega Sy operator, where is the y component of spin operator. The state of the system t equals to 0 is psi t equals to 0 equal to plus the where instead plus minus h bar by 2 plus minus. So then what is the probability of getting the value minus h bar of 2 when sz is measured after time t. So we have to calculate this probability. So yeah. So what is given right here? So you have a spin-off quantum particle uh, in presence of magnetic field B, whose energy or the Hamiltonian is given this way. So where the Sy is the y component of spin operator. Sy is your spin operator, and so at t equals to 0 initially, when you measured the state of the uh, this quantum particle, the spin of particle, you found out that you measured the z component of the spin on the state you applied on the state. You found out that it is plus s bar by 2. So it will be it is plus s bar by 2 or either minus s bar by 2. So what this plus and minus tells you that if you have a uh, so this plus uh, denotes half half, and this minus denotes half minus half. So this is what the same this is SMS at the beginning, which I was telling that the spin eigenstates are denoted as this way SMS, just like how you denote LM for the orbital angular momentum operators L square, Lx, Ly. So same way for S square, Sx, and Sy, you use this uh, notation. The, right. Yeah. Then what you have? So when you have spin half, when S is equals to half, then ms can be either ms can be minus half or half. So as I said, like your m value goes from like if you have lm, then m value goes from minus l to l. Same way, if you have sms, your ms goes from minus s to s. So same way, uh, uh, so so if you take this thing, you will find two states for the given spin-off particle. It would be either uh, half half or it would be half minus half. So yeah, this is your SMS. So you have two states. So initially, uh, when you measured the SZ operator, you found out that remember recall that at the beginning we saw when SZ operator x on SMS, it gives you uh, ms h bar SMS. So, when this SZ operator, initially when it detects on plus or minus, as I said, plus means half half, then you will get plus h bar by 2, ms is half, so h bar by 2. So when it acts on minus 1, or when this minus state, so that means half or minus half. So when sz will act on this half minus half, you will get minus h bar by 2, half minus 1. So right, so using this idea, so that is the initial state. So initially when you measured the z component of spin operator for the given particle, given spin up particle, you found either the particle is in this state or in this state. But then you have to calculate what is the probability of getting minus h bar by 2 when sz is measured after time t. I mean, uh, so yeah, the initially at t equals to 0, the particle was in plus state, this state. The particle was in was in this state. Now, after time t, the particle can be in this state, or again it could be in this state. But you have to calculate. You have to take that time where the particle would be in this state, and if it is in this state, then what is the probability at that time, at time t, that particle will go from plus state to minus state. So basically, the particle will go from this half of state to minus half state. So initially, when you measured sz, you found out that particle was uh, h bar by 2 plus. But after a time t, at time t equal to t, so this is at t equal to 0, when you measure sz, you get minus. So this is what the question is telling. So then, if it is so, if time equal t equal to t, your measure state is minus, then what is the probability that it went from plus to minus? Yeah. So in question it is given that your h is minus omega sy, your Hamiltonian. So uh, right, your Sx operator, you can write it as uh, let me see. Okay, uh, you can check this in this Sx Sy Sz in terms of matrix form. You can write this as 0 1 1 0. Sy you can write it as h bar by 2, 0 minus I 0, and Sz These are also called Pauli matrices. 1 0 0 -1. So uh, if you calculate the eigenstate of this S set, then uh, you will find that the eigenstate would be uh, either h bar by 2. We will get two eigenvalue corresponding to eigenstates. So these are your eigenvalue, or let me write this way: lambda of S set, their eigenvalue, uh, that is h bar by 2 minus h bar by 2, and there are eigenstate. Uh, write this. Let's write this state as some psi of S set will be 1 0 0 1. So these are just how you normally calculate eigenvalues and eigenvector for a matrix. You take this matrix and you calculate that you will get h bar by 2 minus h bar by 2 as the eigenvalues, and corresponding eigenvectors are 1 0 0 1. So this is only represented as uh, plus vector. I mean, you can denote it as plus, and you can denote it as minus, right? So same way you calculate eigenvalues for Sy and eigenvectors, you will get h bar by 2 minus h bar by 2 same, and again uh, you will get uh, yeah, the eigenvectors you will get 1 over root 2 1 iota. Just solve how you calculate eigenvector for a matrix. You will get it 1 minus then same you can calculate for uh, Sx operator. So you'll again get h bar 2 minus h bar by 2. Then eigenvectors are 1 by root 2, 1, 1, 1 by root 2, 1 minus 1. Then, yeah, coming back to our question. So, psi t equals to 0, we have this state. So, this is half, half, or this is 1, 0 for the sz. This is what we have. Then, uh, right, at psi t equal to t, we will have some other state, uh, and uh, to calculate probability, we basically have to take the inner product, that is uh, psi t equal to t and psi t equal to 0, and you take the mod square, that will give you the probability. So so to do that, uh, again what we can do, uh, set psi t equal to 0, this plus which we have written, we can again re-express. Uh, I can write it as plus C1 uh, phi 1 plus C2 phi 2, where this phi 1 phi 2 They are now uh, eigenstates of Sy. What I'm saying, this plus was the eigenstate of Sz. Like I'm denoting only this as plus, so they are the eigenstate of eigenvector of this matrix. But I'm expressing this in terms of uh, eigenvectors of Sy, uh, which are eigen these are eigenvectors of Sy matrix. So I can express that plus vector in terms of some linear combination of phi 1 and phi 2. So suppose, uh, yeah, this phi 1 and phi 2, uh, yeah, let's call this as phi 1, this is phi 1, phi 2. Then uh, I can calculate what are C1 and C2. So I can calculate phi 1 plus, if I take the inner product, then I get half 1 minus 1, 1 0. That will give me 1 over square root. And same way C2, if I calculate, I can get 5, 5 2 I have to take inner product. Then that will give me 1 plus I, 1 0. This will give me 1 over square root. Now I got initial state. So the initial state is 1 by root 2 phi 1 plus 1 by root 2 phi 2. Now I have to check what is psi at t equal to t. So at t equal to t, uh, I know that I can use this evolution operator, that is h t psi t equal to 0. So to evolve a initial state, you use this initial operator, evolution operator. So if I operate this, I will get uh, 1 over square root 2 e to the power minus I h bar e1 t phi 1 plus 1 over square root 2 e to the power minus I h bar e2 t phi 2. So where I am considering h of phi 1 gives me e1 phi 1, and h of phi 2 gives me e2 phi 2. Then uh, if you see in the question right here, the Hamiltonian, which was initially given, h is equals to minus omega sy. So using that, I can do, like, basically I can write uh, yeah, e to the power minus omega sy, that is I omega by 2 t phi 1, uh, basically here maybe it is not good idea to write here. uh, I mean this E1 E2, like in uh, So in question, h is given as minus omega sy operator. So that means minus omega sy operator on phi 1. So uh, this will give minus omega uh, sy operator when it acts on phi 1, it will give uh, h bar by 2 phi 1, because uh, you see the eigenvalue is s bar by 2. So when you operate sy on this phi 1, you get h bar by 2 phi 1, and minus s bar by 2 when you operate on phi 2. So using that information, so same way you will get h acting on phi 2, you get uh, plus omega h bar by 2 phi 2, right? And yeah, since there is h bar in the denominator, the h bar will basically cancel out. So let me write this as h, or minus omega sy into t, minus omega sy t. Then yeah, you have this. Then let me write phi 1. Phi 1 is the complete column vector, which is 1 by square root 2, 1 I by square root 2, then plus half, or basically plus 1 over square root 2, then minus I omega by 2 times t, then 1 over square root 2, then minus I over square root 2. Yeah, then you solve this, you will get psi of t as uh, basically you will get cos omega t minus sin omega t. So how you are getting cos sine? Because if you add them, you know this relation that uh, so when so this is our these are from Euler relation. This is basically cos omega t. And when you have this by 2 iota, this is sine omega. So using that, I'm getting cos and sine there. Yeah. Then uh, yeah, fine. Then we have evolved our system. So we have psi t equal to 0. We had this. This is psi t equal to 0. And now this is psi t. I mean, t equals to t. This is t equals to t. Then we basically have to take the inner product to uh, calculate the probability. So uh, let me write this properly again. Psi of 0. Initially we had uh, plus, this was 1 0. After t, psi t becomes cos omega t minus sin omega t. Uh, right now, when you measure sz, what is the probability of getting minus h bar by 2? That is this minus state. So uh, to get that, you take minus and psi of t inner product square. That will give the probability. So you have 0 1 because plus is defined as 1 0 and minus is defined as 0 1. Then you have cos omega t and sin omega t. I think, yeah, this like I've done right, right. So here it will be by 2. I have missed by 2. So if this is by 2, then this will be by 2. Right. So by 2. Right. So if you calculate this, you will get sine square omega t by 2. So yeah, this was a bit complicated. Well, there are a lot of things involved in it. So try to go through this once. If you could not get, let me know your problem. Uh, yeah, there are many things involved here. So try to go through this. But yeah, this kind of problem should be very useful to understand many things ahead. Yeah, is there any particular doubt or related to this question or something more on this, or uh, yeah, do you have any question, Nitin?
Hello.
Yeah, yeah.
Sir, I have a question other than this.
Okay.
You have suggested that there are book of Sakurai. So Sakurai has a two options. One is advanced quantum mechanics and another is modern quantum mechanics. So which one should I choose?
I think Sakurai would be not good idea to start. So let's start with Griffith.
Griffiths, right? And in next phase, I should go for advanced quantum mechanics by Sakurai.
Yeah, yeah, yeah.
Not
That is.
not modern, but the last version, advanced quantum mechanics.
Uh, Maybe try start with modern.
So both the books are substantially different, or they are near about same.
I mean, there are few more inclusion in the modern quantum, or I think in the advanced quantum mechanics. But I would suggest let's start with let's go step by step gradually. Start with Griffith and Zetley, then maybe let's say try Shankar, then
Sure,
Sakurai.
sure, sure, sure,
Yeah. So,
sure,
so first of all, try to cover as much as basics you can from Griffiths.
sure.
Okay, then if there's any other doubt anymore.
No, sir.
Okay, so then probably we are also uh, going. I mean, already the time is up, so we can probably uh, end this session if you do not have any other question.
Okay, sir. Bye.
Okay, okay. Then yeah, see you again next week. Okay.
Sure.
Yeah, bye. Thanks.